Hello everyone. Today I will introduce the convex optimization applications in approximations and fitting. It includes four main applications: norm approximations, least norms problems, regularized approximations, and low box approximation. The first application is norm approximation. This form is the simplest norm approximation problem. This problem is convex and is solvable. There is always at least one optimal solution. Its optimal value is 0 if and only if the B vectors are in the real n matrix. These problems can be interpreted as three kinds of applications. In the geometric interpretations, we see that solving the norm approximation problems is equivalent to computing a projection of the B vector onto the A matrix. In an estimation problem, the problem is to make a sensible guess of the x value when the y value is given. The third application is in optimal designs. In this problem, the goal is to choose a vector of the desired variable x to achieve the desired results. Here is the example. We can attack these equivalent problems, which is called the least square approximation problems, by squaring the original objective functions. When the L infinite norm is used, the norm approximation problems is called the Chebyshev approximation problems. But when the L1 norm is used, the norm approximation problems is called the sum of residues approximation. Here we consider useful generalizations of the LP norm approximation problems. We call it the penalty function approximations. We can see that the objective depends only on the amplitudes distributions of the residues. Each component in the objective, the omega r's, is called the penalty functions. We assume that each component's function is convex. So the penalty function approximation problems is obviously a convex optimization problems. And the below are the plots of some common penalty functions. And here are four figures so that the four associated penalty functions and the amplitude distribution of the optimal residues for these four penalty approximations. Another example is the low box least squares. We also call it the Hubble's penalty functions. These penalty functions agree with the least square penalty function for residues smaller than m. The left figure is the Hubble penalty functions. and the right figure is the outlier penalty functions. These two figures are different, designed by the different aims or the affine functions. The second application is the least norm problems. The objective function of these problems is to minimize the norm of x vector. There are also three kinds of interpretations. In geometric interpretations, we interpret the objective function as the distance between the x and the point 0. The least known problems finds the points in the affine set, uh, which can achieve the minimum distance to the point zeros. In the estimations interpretations, we assume that x is a vector of the parameters to be estimated. So the least known problem is to choose the estimate of the parameter vectors x. We choose the one which is the smallest one among all the parameter vectors. In design interpretations, the x vector are the design variables among all the designs. The least norms problems choose the smallest design, which is measured by the norm. Here is an example of the most common least norms problems. By squaring the objectives, we obtain the equivalent problems. The unique solution of these objectives is called the least square solution. Here is the extensions of the least squares problems. It is the variations on the least norm problems. We call it the least penalty problems. It is also a convex penalty functions. The third application is regularized approximations. The goal of this objective is to find a vector x which is small and also makes the residues. A matrix multiplies x vector minus b vector small. This problem has two objectives. The first objective is to measure the size of the residues. The second is to measure the size of the x. There are also three kinds of interpretation of these applications. In an estimation settings, the actual terms, x norms, can be interpreted as the prior knowledges in which x norms is not too large. In an optimal design setting, the actual terms x the cost of using large value of the design variables. In a low box approximations, the small x norms can also reflect a modeling issues. By squaring the objective function of the regularizations, we obtain the projective optimization problems. It is called the Tikhonov regularization problems. And the solutions to this problem requires no rank assumptions on the matrix A. Here is an example of the optimal input design. The goal of this objective is to choose the input sequence N to achieve the several goals. For example, we can check the error with the desired outputs. We can also measure the magnitudes of the inputs or measure the variations of the inputs. Uh, from through these three techniques, we can check the desired outputs using a small and slowly varying input signals. These are 6 figures showing the optimal inputs and the corresponding output for 3 values of the regularization parameter alpha and gammas. It can also be used in signal reconstructions. This objective function is used to measure the roughness or the lack of smoothness of the estimate X bar. The problem is to seek the signals that are close to the correct signals. These are 2 variations of the reconstruction problems. Uh, this is the figures of projective smoothing examples. The left figure shows the original signals and the corrected signal. The right figure shows the reconstruction signals with different solutions. We can see that when the smoothing function equals to V, it achieves the best reconstructions. Here are also an example of the total variation reconstructions. Also, the left are the original signal and the corrected signals, and the right are the three difference applies different parameter vectors. We can see that the middle smooth signals give the best compromise. So we can say that the total variation smoothing preserves the sharp transitions in signal. Here is the fourth application. The problem is to minimize the objectives with uncertain A matrix. There are 2 approaches. The first is to assume the matrix A is a random variable, so it is equivalent to minimize the expected value of the norm of the objective functions. It is also possible to model the variations in the matrix A using a set-based worst-case approach. In this figure, the plot shows that the approximate solutions is sensitive to the variations in the parameter mu. The nominal solutions achieves the smallest residues when u equals to 0, but it is quite sensitive to the parameter variations. And it gives much larger residues as u derive from 0 and approaches -1 or 1. The worst case solution has a larger residues with when the mu equals to 0, but its residues do not rise much when the u varies over the intervals between -1 and 1. The stochastic low-box approximation solution is in between. Some variations on the stochastic low-box approximation problems are tractable. For example, consider these stochastic low-box least square problems. The norm is the Euclidean norms. By explicit expressions, we can see that this problem has the form of a nebulous least square problems. Actually, this makes sense. When the matrix A is subject to a variations, the vector A matrix multiplies x vectors will have more variations with the larger x. This observation gives us another interpretation of the Tikhonov regularization least square problems. And for the worst case low box approximation problems, it is to minimize the worst case error. In this objective, the variable is x, and the problems are the problems data are the b and the set a. When the set a is the singleton, the low box approximation problems reduce to the basic norms approximation problems. The low box approximation problem arises in many contexts and applications. In an estimation setting, the set A gives our uncertainties in the linear relationships between the estimate results and the Maxwell's vectors. In an optimal design setting, the variations can represent uncertainty of the linear equations that relate the design variable x to the results vector A multiplies x. Okay, that's all my presentation. Thank you.